Hello, everyone. So we're going to get going on the second part of our derivatives lecture today. And we're going to actually finally get to some business applications here. So we're going to talk about profit and cost and things of that nature. We're also going to talk a little bit more about tangent lines and how to find those. And then we're going to wrap up pretty quickly with this idea of differentiability. So let's go ahead and jump right on in. And let's start talking about some business applications. So now that we've heard this word derivative before, we can start talking about business applications. And in particular, the three things that we're generally interested about are revenue, cost, and profit. And so if we've got revenue, cost, and profit, those are fairly straightforward, ideas themselves. Profit, you could find that by looking at your revenue and then subtracting off your cost. Your revenue function, your cost functions are generally given to you. But now what we can do is we can add this word marginal in front of these words. And when we do that, that generally just means derivative. So for some formal definitions, marginal revenue is the instantaneous rate of change of your revenue function. And then same for cost and profit. Marginal cost is the instantaneous rate of change of your cost. Marginal profit is the instantaneous rate of change of your profit. So basically putting this word marginal in front of one of these terms, it just means take a derivative. And so notationally, we saw before that we can use f prime of x to denote a derivative. So if I have a revenue function r of x, or a cost function c of x, or a profit function p of x, I can just denote their derivatives by just adding these little primes right there. So I'd have r prime of x, c prime of x, and lastly, p prime of x. And that's going to give us that sort of notation for marginal blank, marginal revenue, marginal cost, marginal profit. And like we saw last time, we did that example with f of x equals x squared, and we took a derivative of it using the limit definition. So for now, if I give you a revenue, cost, or profit function, and I say, hey, find the marginal revenue, cost, or profit function, then you have to do the limit definition of the derivative just like we've been doing, and that'll give you that answer right there. So let's go into talking about marginal cost, and I guess if you want to call this an example, we can. If I have a linear cost function, not all cost functions are linear, but if I have a linear cost function, and so it looks like this mx plus b, it looks like a line that we're used to. In that case, we can look at this b and we can say that those are the fixed costs, and we can look at m and we can call that the marginal cost. And there's a reason that m is called marginal cost, and it's because if you actually take the derivative of this function here, you're going to get just m. Let's go ahead and do that really quickly, just so we can convince ourselves of that fact. So if I have f of x, well, let's go ahead and call it c of x. C of x equals mx plus b. And I say, hey, I want to find c prime of x. What the heck is c prime? Well, I can go on and I can just do the limit definition. So c prime of x is going to be equal to the limit as h approaches 0 of c of x plus h minus c of x all over h. And if I plug in for c, I'm going to get m multiplied by, and now not an x, but an x plus h. So x plus h is my input. So everywhere that I see an x, I replace it with an x plus h. And then here I just have mx plus b. Be careful here. I like to put some parentheses around all this just to make it very clear. If I don't put the parentheses over here on this side right here, then if I just write minus mx plus b, that b is added as opposed to subtracted. And we don't want that. We want it all to be subtracted. All this is divided by h. So if we work this out, I'm going to have mx plus mh, so I'm distributing that m, plus a b, minus mx, minus a b, just distributing that negative sign. We get some cancellation here. mx and mx cancel, b and b cancel. And I have the limit as h approaches 0 of mh over h. The h's will cancel. And we end up with just the limit as h approaches 0 of m. And we can do our direct substitution there and just get m. And then we're good. So we've confirmed that is in fact our answer right there. And so that's exactly why we call, in the case of this linear cost function, that's exactly why we call that that m marginal cost, because that's exactly what it is. It is the marginal cost, C prime. Great, so we've got that. Let's move on to the definition of average cost. So average cost, no derivatives involved here. We're going to denote this by C bar. So we'll call this little bar, this little line above it, C bar of x. And all that is it's C of x then divided by x. And so what this actually is doing is you're taking your cost function and you're dividing it by the number of goods that you're making, your quantity, if you will. Sometimes you'll see this formula written C bar of Q, Q standing for quantity. Doesn't matter either way, X or Q, you can use either for quantity. But we've got that here. So average cost, that's going to be the cost per unit that you make, because I'm taking the total cost and I'm dividing it by the number of units that I'm producing. So that's average cost. What a lot of economists actually care more about is marginal average cost. And again, like I've said, when we use that word marginal, we just tack on derivative, right? That's all we mean is just derivative. So I have C bar prime of x, and be careful about the order of things here. What I'm doing is I am taking the cost function, I'm dividing it by x to give me average cost, then I'm taking a derivative. So some people, what they'll do is they'll take a derivative of the cost function, and then they'll divide it by x. And that's out of order. That would actually be average marginal cost, which is very different from marginal average cost. So the order of that matters. So make sure that you find average cost first, and then you take a derivative. And what I'm realizing here now is actually I'm using a different notation that you guys haven't seen yet. So let's go ahead and talk about this. This prime right here, we've said that that means take a derivative. But just as equivalently, I can use this ddx. And if I say ddx and then I have a bunch of stuff in parentheses after it, though that stuff in parentheses is what I take a derivative of. So notationally, I could write one of two things. I could write f prime of x, or I can write ddx of f of x. There's reasons to use one over the other. We'll see that a bit later in the course. For now, I don't really want to talk too much about that, but you can use either of these notations, and clearly I'm using one of those notations here with that ddx. And there we go. So we've got marginal average cost as well as average cost. So there's another sort of business application that you could have. So let's move on. We're going to move away from the business now, and we're going to talk about how to find a tangent line. And I know there's a whole lot of letters and everything here. Don't worry about all that now. Let's just talk about it. So we've seen that the slope of a tangent line is, and let's open up a new slide. So we've already seen before that the slope of a tangent line, that's the derivative, right? We have that limit definition of the derivative. Limit is x, or limit as h approaches 0 of f of x plus h minus f of x all over h. We got all that good stuff. That's fine. But the slope of the tangent line is just the derivative, which, writing that shorthand, it's just f prime. And we're going to do this at the particular point C, right? So maybe I should say the slope of a tangent line at a point x equals C. That's just the derivative. which is given by f prime of c. So right there, we have a formula for the slope of that tangent line. So remember, when just going back to algebra, if we want to find the equation of any line, so forget calculus for a second, we just want to find the equation of a line, that ends up, we can use point slope form for this equation. For any line equation, you can use point slope form. And as long as you have a point given by x naught comma y naught, and you have a slope given by m, this is the equation of your line right there. So you've got your point and your slope, and that's all fine and dandy. So what I'm going to do is I'm going to use this point slope form to write the equation of this tangent line. So let's take a look here as well and recognize that I've got f prime of c as the slope of the tangent line. So that's going to be m. We already have that figured out. All we're left with is how do we find this point x naught, y naught. And let's go to a picture and take a look at this. We've seen this graph before where I have my function and I have a tangent line that just touches it at that one little point. It just barely kisses it right there. And this is at a point x equals c, and the y value is f of c. So if I want to find the equation of this line, I'm going to recognize, using point slope form, that my y coordinate is given by f of c. You can see that right on the graph here. This coordinate, this is a point on the line, on the tangent line in red. And so I can use that y coordinate there, and that's a point on that tangent line. Likewise, we just said and we just saw that we can say the slope of this tangent line is given by f prime of c. We haven't calculated it explicitly, but you could if you were to carry out the limit definition of the derivative. And then we've got our x coordinate just given by c. You can see that right there, c right there. For that point on the tangent line, we've got our x coordinate c. So all I've done to get from here to here is I've just added f of c to each side. And voila, we have the equation of a tangent line. So if I wanted you to find the equation of a tangent line, so if I gave you a function and a point, so maybe I give you a function like f of x equals x squared, and then I say at the point x equals 3. I could say, hey, find the equation of the tangent line of x squared at x equals 3. Let's go ahead and do that. And I'm gonna skip some work here and there as we see fit, because we've actually already taken this derivative before. But let's say I pose a question to you, and the question is find the equation of the tangent line so the tangent line of f of x equals x squared at the point x equals 3. So we actually already found the derivative of x squared in a previous lecture. So I'm just going to utilize that here. You could carry out the work with the limit definition of the derivative. I'll go ahead and write out that first step. So f prime of x is going to be the limit as h approaches 0 of x plus h squared minus x squared all over h. And then we did all this work before, and we ended up with just 2x there. So that's great. That's fantastic. We've got our formula there for our derivative. Now, I need to find the slope at that point. And so I want to do f prime of 3 here. And if I do that, we can just take our 2x, which is already our derivative, and we can just plug in 3 and we can get 6. And so this right here, this is the slope of f of x equals x squared at x equals 3. It's the slope of the tangent line. Those are the same thing, right? And that's great. So we've got the slope of the tangent line. Now the only thing we need is the point, right? And we actually already have the x value, so we might as well just carry on and find the y value. So let's go ahead and do that. Let's say that f of 3 is equal to 3 squared, which is equal to 9. So what we've got there is we have the point 3, 9, and that point is on both the function and the tangent line. You can see that by this picture here, right? This point that we're looking at, that point is touching both the tangent line and the curve, the function itself. So we've got that. Now we're just going to use that sort of equation of a line, right? This is point slope form, just going back to algebra. We have the slope in orange of 6. We've got the coordinate point in the work in the pink, and that coordinate point is 3, 9. So if we just wrap this up, we can just write that our equation, let's do a different color there, y minus the y coordinate is 9 equals the slope 6 multiplied by x minus the x coordinate 3. That's just me doing y minus y naught equals m times x minus x naught. And that's our answer right there. We've got this y minus 9 equals 6 times x minus 3. If you wanted to simplify that, you could write that in slope-intercept form. I'm not too picky about that. This is a perfectly good equation for a line, and we're on our merry way. So that's tangent lines. And it's really just point slope form, but now we have a different way of calculating the slope. Rather than having to do rise over run and all that stuff, we can just take a derivative. So lastly, what I want to talk about is differentiability. And this actually it kind of has a similar feel to continuity. They're different things, but the feel of it is the same. We've got 3 conditions, and in order for a function to be differentiable, all of these conditions have to be satisfied. And so the first condition here is that f of x has to be continuous. So within this condition for differentiability, you have 3 more conditions to look at. And those are the conditions of continuity. And let's remind ourselves, f of c exists, limit as x approaches c of f of x exists, and these 2 things better be equal to each other. So if a function is not continuous, then it is not differentiable. There we go. Limit equals the function. The second condition is that f of x has to be smooth. And when I say that word smooth, all I mean is there's no sharp corners. I'll draw a picture of this in just a second so you'll know what I'm talking about. But there can't be any jagged edges or anything to the function. And the last thing, but definitely not least, is that the function cannot have a vertical tangent line. And I'll draw a graph of that as well so we can see. So let me open up a new slide here, and we'll take a look at some examples of functions and where they fail to be differentiable. So let's go ahead, let's draw, I'm just going to draw one big function here. So coming along with this function, maybe it keeps going on. Just going to look at it on this interval. So we've got a couple interesting things here. There's some weird stuff going on here. I'm going to call that A. We've got some weird stuff going on here. I'm going to call that B. And we've also got something weird going on right here. I'm going to call that C. Let's take a look at each one of these. So at A, that you might be able to tell, that's just a sharp corner, right? So what's happening here is our function is coming up here, it's all smooth, and then it just has a sharp jagged edge and it curves like this. An example of this in a sort of a similar function is f of x equals absolute value of x. that guy looks like so, right? We've got that jagged corner there. So here we've got a jagged corner, and this is exactly the idea of a function not being smooth. And why we say this function is not differentiable at that point, it has to do with tangent lines. So what we really mean when we say a function is differentiable is we mean that it's going to have a single tangent line. But let's go ahead and look here. I would argue that this green is a tangent line at that point A. It only touches the function at one particular point, and it matches the slope at that point. But also, the purple is a tangent line. It only touches the red function at that exact point. And I could keep doing this really as many times as I wanted to. There's a line there in yellow that only touches the curve, the function in red at that one point. So that's satisfying the definition of a tangent line. But I've got multiple tangent lines here, and that's what's bad. That's what we don't like here. So that's why we say this function is not differentiable at A. So if we move on, let's go ahead and look at B. If we look at point B, the function isn't even continuous there. I mean, you can tell the limit doesn't exist, right? If I were to draw this with my pen, I have to lift my pen up to jump up higher and continue the rest of it. And so this function isn't even continuous. So if I asked you to draw a tangent line, there's just no way to draw a tangent line, because what point would you even use? I mean, the function isn't even continuous there. So that's a reason why B is not differentiable. There's just no way to draw a tangent line at x equals B. And then C, this is that example of having a vertical tangent line. So I'm going to go ahead, I'm going to erase some of these dashed lines right there. If I were to draw a tangent line at this particular point here, it would go straight up and down. And the reason we don't like that is because the slope of this line is infinity. And so if we were to try and write the equation of that tangent line, you couldn't, because remember, we have our line equation, y minus y naught equals m times x minus x naught. So if m isn't even a number, if it's infinity, that's just bad. We just can't find the equation of that tangent line. And so that's why we would say this function is not differentiable at that point x equals c. It's because the tangent line doesn't really work out there. We don't have a nice, clean, and concise way of writing that tangent line there. So that's great. We've got differentiability there. This is an example of a function that is not differentiable at these three particular points. It is differentiable everywhere else, but generally when we ask about differentiability, we just ask for, hey, where is it not differentiable? Same thing with continuity, right? We just say, hey, where is this function discontinuous? So here we just want to know, where is it not differentiable? All right, I'm going to go ahead and leave it at that, and we'll move on to doing some derivatives graphically next time.